right here without looking at the board and reading what it says. Mr. Weber is famous for that. What does geometric mean mean? Okay, so first off, if you heard that, you would think probably the mean, and the mean back in the day was what? The average, right? Okay, so what do you think the geometric mean is going to be? It's going to be maybe an average or something, right? But, kind of not, all right? So basically what's going to happen here is we're going to look at something and we're going to still try to form a proportion. So anytime that from here on out that you hear geometric mean, okay, you still want to form a proportion. So we're still going to have a fraction equal to a fraction. All right? And basically what's going to happen here is they're going to say find the geometric mean between two numbers. And for argument's sake, in this first one, we're going to call our two numbers A and B. All right? So what's going to happen here is you're going to form a proportion with those two numbers. And the two numbers that they give you are always going to be diagonal to each other. It honestly doesn't matter which way you put them. Okay? In the other diagonal, there's going to always be some number, but in this case, we're going to call it x. That is exactly the same number. So basically, when you want to do the geometric mean, you're going to make sure that one of your diagonals is always the same number. And that's the key to this whole thing at the beginning. Because if I would end up doing this now, what would I do?
AB cross multiplying.
So I get AB is equal to what?
X squared.
X squared. And how do you make something that's squared not squared anymore? I'm going to take the square root. So I would take the square root of this side and the square root of this side, and I'd get x equals the square root of AB, right? So realistically, this is what you're going to try to do in the first section today. They're going to give you two numbers. In the other diagonal, you're going to put some variable, okay? And then we're going to remember that my final answer should be something maybe underneath of a radical, all right? So in some cases, we might have to reduce our radicals. Now again, the last couple of years, we've kind of got laxed on this because, well, we went through the whole section of kind of missing this for some of you in algebra. Okay, so everybody understand what we were talking about a radical? Yeah. Okay, and when we're going to reduce a radical, that would be something like this. If I had the square root of 60, okay? So if I look at the square root of 60, to reduce this, obviously I can punch it into my calculator, right? Can I take the square root of 60? Yes, I can always take the square root of any number, right? I can punch it into my calculator and get a decimal. But again, most of the time I would tell you to leave it as a radical instead of punching it in your calculator and getting a decimal. So that means you might have to reduce your radical. And if I'm going to reduce my radical, it means that I'm going to find a factor that's what?
Perfect square.
There you go. Find a perfect square factor. Now, does everybody understand what that means? First off, what's a factor?
Number times number equals factor.
The numbers that are multiplied together to get the number that you want are the factors of it. So what's a perfect square?
Oh, it's like
9.
16, 4.
So how would you explain it?
A number times itself.
Okay, but if you take the square root of that number, you get what?
Whole number.
A whole number. It doesn't have a decimal. So the square root of 60, is that a perfect square?
No.
No, right? Perfect squares are, like you said,
16.
we start at the beginning.
64.
1 is the very first one. A lot of people forget about 1. But why is it a perfect square? Because basically whatever I take, when I can take some number and square it, I get this number, right? So, remember way back when you did algebra?
Yeah.
You talked about inverse operations? Inverse meaning what? Opposite, right? So addition and subtraction went together, multiplication and addition went together. Well now, square roots or radicals and squares go together. The exponent, those are inverses of each other, right? So how do I get rid of something squared? I take the square root of it. That's an inverse operation also. It's just more advanced than PEMDAS. So we wait for it a little bit. So, 1, what else? 4,
9, 16, 25, 56,
49,
64,
81, 100, 121,
121,
144, 132,
144 is 12, 13,
You said that
169, 14,
196.
196, 15,
225.
225. Ladies and gentlemen, you should definitely know through 15. Okay? 16,
256.
17,
234.
I just said
513.
no, you're way too high now. Obviously, then the other ones that are probably kind of keys, 20,
400.
425,
1,200.
625. Okay? Those are kind of key ones. All right? So, when we're talking about simplifying a radical, we're talking about taking this number and finding a perfect square into it. Okay? So, a lot of people, when they do this, they're like, well, obviously my factors are 6 times 10. You're right. The factors of 60 are 6 and 10. But are 6 and 10 a perfect square? No, so we don't care about 6 and 10 in this aspect. Okay, so we don't care about this one. We want factors that multiply together give me 60, but one of them's a perfect square. So we'd say 4 times what?
15.
4 times 15. 4 times 12 is 48. Okay? So
Take a
then,
guess.
once you find your factors, where one of them's a perfect square, then I take the square root of that number. If I take the square root of that number, the answer goes where? To the outside. So this becomes 2, and then I have to ask myself, can I take the square root of 15?
No.
No. Can I break 15 down into a perfect square that I could take?
No.
No, because the only 2 factors of 15 are what?
3, 5.
3 times 5, right? So then my 15 stays inside, and this right here, even though you might not believe it, is way more simple than you punching the square root of 60 into your calculator. Okay? When you get into algebra 2 or trig or calculus, this would be way easier to use. Okay? Everybody good with that? Need to do anything else with that? Okay. So that's what we're talking about with reducing radicals. Okay, so here they go. They're just going to simply tell you to find the geometric mean between these 2 numbers. So the first one is 2 and 50. So if they give you 2 numbers, you're simply going to set up this right here where 2 and 50 are either A or B, and you have your X's on your other diagram. Okay? So you simply just write it out. The X's always have to be the same thing. And now I'm ready to do it. X times X is?
X squared.
2 times 50 is?
100.
So what's X?
10,000.
Now. No, what? We're taking the square root of it. Right? Now, again, this is especially for ISAFs coming up. If I take the square root of something, I really should have what?
Plus or minus.
2 answers every single time, right? Realize, when they give you an equation like this, the exponent on the variable tells you how many answers you should end up with. So if this is x cubed sometime, you should actually end up with 3 answers. By factoring it in or something. You said how, right?
Yeah, I said how.
Well, like this right here, I'm going to get 2 answers because it's plus and minus 10.
Yeah, how do you get,
So there's 2 answers.
yeah, how do you get 3 though?
I would factor it some other way. We just don't have a problem with that. Okay? So that one was pretty easy, right? Then we get into something like this, where my numbers are 3 squared root of 2 over 7. And 5 squared root of 2 over 7, I believe.
Yeah.
So again, don't get frustrated just because they have radicals. You're going to do the exact same thing. You're going to put it over x. And then you're going to have x over the other one. Remember, when you multiply radicals, what's the key? Outsides times outsides and insides times insides. Everybody understand what I'm saying there? So when I do this right here, I still get x squared on my one diagonal. On my other diagonal, I'm going to have 3 square root of 2 over 7 times 5 square root of 2 over 7. Now again, because I'm multiplying by fractions, I can look diagonally to see if I can cancel things out. So I can't cancel out the 7s because they're both on the bottom. But I'm multiplying this way. Okay, so when I multiply, I'm going to now multiply straight across the top and straight across the bottom. So on the top, I'm again, outsides by outsides and inside by insides. That means 3 times 5 is 15. And what's the square root of 2 times the square root of 2? 2. It's really the square root of 4, but the square root of 4 is 2, right? So when I take a radical times itself, I really get what? That number. Okay, but that number then gets busted out of that radical sign. So it's really 15 times 2 on the top. On the bottom, I get what? 49. So realistically, I get 30 over 49. Now I'm ready to take the square root, right? I'm going to take the square root of both sides. Now this is where I get to cheat a little bit. The square root of something squared just busts that or breaks that square root now. Okay? Here, remember, anytime that you have a radical and there's a fraction, you can give the fraction its own radical on the top and on the bottom. So this, realistically, I can rewrite as the square root of 30 over the square root of 49. Okay? Now, you don't have to rewrite it, but that's realistically what you can do. Okay? So then I'm gonna do the math real quick, and I'm going to say, well, I know what the square root of 49 is. Yeah. And then I'm going to ask myself, is there a perfect square? Don't say anything out loud. Is there a perfect square in 30 as one of its factors? So you got to start thinking about the factors of 30, right? 2 times 15. 3 times 10. 4 doesn't work, right? 5 times 6. So none of them work, right? So my answer in this case is
30 over the square root of 7.
The square root of 30 over 7. Now this is really important too. Make sure what's underneath the radical is only what's underneath the radical. So don't get sloppy and do this thing right here, right? Because we only want the square root of 30 to be underneath the radical. So make sure that you get your fraction bar across there. Make sense to everybody? So this is my geometric mean. Okay? Whatever numbers they give to you, they're going to be one diagonal, the other diagonals, any variable you want. I just used x. You can use whatever you want. Okay?
Why does it stay to 2, 15 times 2, not...
Because this right here was the square root of 2 times the square root of 2. So if I do the inside times the inside, I really get the square root of 4. But the square root of 4 is 2.
Oh.
And so basically I took the square root so it goes outside, it erases the radical, and then I multiply the 2 numbers that are on the outside. Okay? So anytime that you take a radical times itself, so if I took the square root of 7 times the square root of 7, it's just 7.
Okay.
Realistically, it's the square root of 49, but the square root of 49 is 7. So we're skipping to one step. And that's just one of those kind of mathematical cheats that you can remember. Okay? All right, here? Okay. So, we get back to theorems. Theorem 8.1. Again, a lot of words in theorem 8.1. I don't know if you want to write it down. Okay? Totally up to you. It says, think about this now. If the altitude is drawn to the hypotenuse of a right triangle. Okay? If the altitude is drawn to the hypotenuse of a right triangle. So, if you don't like the words, try to draw the picture. Again, if you want the words are up here on the board, or they're always in the book, right? Again, to me, this is confusing with the words, so I'm not going to write the words. I'm going to draw the picture. Okay? So, if it's talking about a hypotenuse, I have to have a what? I gotta have a right triangle. So, draw a right triangle. I'm gonna do it this way, because it's easier to do what we're gonna do. And then, how do I show everybody that I have a right triangle? I gotta have my box, right? Now again, you don't have to draw it this way necessarily, but it's just a little easier. Now it says, if the altitude is drawn, what is an altitude?
It's when a line from a vertex goes to the other side, forming an angle.
So it's from a vertex to the opposite side. But it says right here, the altitude is drawn to the hypotenuse. So, here's my hypotenuse, right? I know this has to be my hypotenuse because why? It's opposite of my box, or it's along the side. So when I draw my altitude, I'm going to draw this line straight down this way. And it also has to make what? 90-degree angle. Everybody good there? Here's the biggest oh-ha moment of the day. Come back here and let's write A, B, and C here. Does everybody see that when we drew that right there, we formed a total of 3 triangles? The original one that we had, and then when we drew that line, everybody see a little one over here and a bigger one right here? So really, there's 3 sizes of triangles, a little one, a medium one, and a big one. Everybody good with that? Okay. Let's call this D. So what this says then is the two triangles, I'm going to write this part, because this is what the first sentence says, right? If the altitude is drawn to the hypotenuse. The 2 triangles formed are similar to the original. And each other. So basically, they're saying all 3 of those triangles are similar. So the original triangle was what? Tell me the original triangle. I don't care what version you use. ABC. So, is similar, right? That's my symbol for similar, to triangle. Now, I want you to do this on your own. See if you can do this. What is the medium-sized triangle? So put the vertices of the medium-sized triangle. Everybody see what I'm saying by the medium-sized one? It's this one right over here. Okay? Now put your vertices in order that matches ABC. Remember, because the order matters, right? Where the letters are in the sequence of 3 tells you how they match up. And then you're going to have similar to the little triangle. So you're going to do the medium triangle and then the little triangle. You're going to use those letters right there. So, who thinks they know this one right here?
CDB.
A, you're saying, is the same thing as C.
I didn't see
Okay, first off, did everybody do ABC?
Yes.
If you didn't do ABC, then you're not going to be the same. Did everybody do the first triangle as ABC? Okay, so does everybody understand what I'm saying, that this medium triangle, so I'm taking this medium triangle right here and I'm pulling it out. And I'm going to flip it over. This side right here is going to go along this side right here. Right? Because see, here's my box, so this has to be the hypotenuse. The hypotenuse has to match up to the hypotenuse. So, is Gabriel right with what he said the first time?
No.
A has to go with what? B.
That's close.
What does B have? I'm asking you to find. Oh, great. That one works good.
That's a good one.
Now I'm going to try to work with this triangle right here. Everybody agree with that? That's my medium triangle. Okay? So, to me, I'm looking at the hypotenuse, because I know this has to be the hypotenuse right here because it's opposite of my angle. Everybody agree with that? So the hypotenuse and the hypotenuse have to match up. So if I have A and C, I also need my hypotenuse to be B and C. So B and C should be in the same spot as A and C.
Oh.
realistically. But what I'm saying is, I'm taking this little blue one and I'm taking it out and I'm flipping it over, so this D goes up to this B. And then I got my shorter side here with my hypotenuse.
Why don't you just flip it? For B, we would have it A. And D would stay the same.
D would stay the
So
same.
you just basically rotate D, and you put B where A is, and C would go where B is.
You're saying this B is gonna go where?
To A.
Cause it
A.
goes the whole big.
Which it does. B goes to A, exactly right, so I'm flipping it this way. Absolutely.
Why does D just stay the same and C goes there?
Cause it has to.
Because D is the right angle, it has to be in the same spot as the right angle of the first one.
Oh.
So B and D have to be in the same spot because they're both the right angle.
Okay.
So in the next one, D is gonna be in the same spot again.
But if you rotate it, then it'd be CD.
No, I'm not rotating, I'm flipping it. I'm basically taking this and flipping it this way. I'm not rotating it, I'm flipping it. Okay?
So the ADB then was.
So the last one then, A is the bottom left-hand corner, so what do we get? A, and then it's D, and then what? B. Okay, right. So a lot of times, if you can't see that in this, I recommend doing this. And people can sometimes see it better. Some people don't like this, so don't do it. Okay? And then they're saying, well, this is my right angle, so this was B. This is my right angle of the middle one, so this is D. And this is my right angle of the little one, so this is A. Or sorry, D again. And then my original long angle was B to A. So my side would have been D to B, and this side would have been D to A. Now, I don't know if that helps you, but sometimes that helps people, especially when we're going to do the geometric mean here of this. Okay? So, the biggest thing is when I draw that altitude, and again, it doesn't have to be necessarily in this orientation. It could have been standing up on that one of those legs and still drawing that altitude. But then the ones that I make are still similar. They're the exact same shape. Okay? Good to go there? Now we get fun. Now we get into the fun side. So, there are 8-2. So basically, we're going to say that pretty much the exact same figure, if you wanted to say. Okay? But again, I don't know if you want the words. The altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. Okay, so if you like words, again, write it down. If you don't like words, this is what that means. Okay? So again, the altitude drawn to the hypotenuse, so I'm still going to draw my altitude. And I know it's an altitude because of the box. Okay? Do you see, like, when I draw this, that it splits this hypotenuse into two sections? Okay? So, when I draw this line right here, this is capital A. Let's actually do it this way. A, B, and let's make this C. From here on out, it's probably easiest to always put your right angle as letter C. Why?
Oh, because Caesar's not obviously thing.
So when we do Pythagorean theorem, this is really a squared plus b squared equals c squared. So a lot of the times that's how they're always drawn. Okay. But does everybody see this now? And let's put D again in here. But I'm going to show this by saying that this is x and this is y. You okay with that? So I'm saying from A to D is x and from D to B is y. So that's what the first sentence means. The altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. Okay? The rest of it says the length of the altitude, the length of the altitude, so let's call this A for altitude. The length of the altitude is the geometric mean. So when it says it's the geometric mean, that automatically tells you that you should draw or make a proportion. And when it says it's the geometric mean, that has to go diagonal to itself. So whatever they tell you is the geometric mean has to be across or diagonal from each other. So in our original geometric means, it would have been the x's.
So it's nice.
In ours right here, it's the a's because that's what they told us. The altitude is the geometric mean.
Is that always gonna be the altitude, the geometric mean, or is it gonna tell us?
No. It's for theorem 8.2, yes, it's always the altitude. Okay? So what does it say? It says it's the geometric mean between the lengths of the two segments of the original hypotenuse. So it's between x and y.
Whatever those lines are.
Whatever this distance is for x, whatever this distance is for y. Okay? So they're either going to give you a, x, or y. They got to give you two out of those three.
So that'd be extra wire.
Yes. And then you're going to plug it into this formula right here, for this proportion. Basically every single time. Okay? After this then, if they ask you to fill out the rest of the triangle, so let's just say then they call this little z. If they ask you to find z in this, what can I do if I know that I found x and I found a, then I can do what? Pythagorean theorem, because I always have a right triangle now. And again, so a lot of this, after you do the geometric mean the first time, you're going to use Pythagorean theorem. So you're going to kind of get sick of this in the next week and a half, 2 weeks. What's my Pythagorean theorem again? And C always has to be my hypotenuse, which is always what?
Opposite.
Diagonal from my box, right? Okay? Diagonal from my box. What time is it here?
10 minutes.
16,
26.
26 gauge.
So, this one right here again, if you don't understand that concept or you can't see it right away, a lot of times this helps again to draw those three triangles, and then you can try to figure out what you're going to put into the proportion. Okay? I want to show you this example. If you write the examples down, then you want to go ahead and do this. If you don't write the examples down, just turn here and see for a second. It says, write a similarity statement identifying the three similar triangles in the figure. So again, all this is doing is what we did right over here. So I just want you to try to visualize or see what you would write down. And again, the order is what matters. Okay? So again, try to do this right now. Write it down. Now, I have no idea if you're capable or able to do this. Oh, that's not what I did. But sometimes that helps if you can do it in 2 different colors. Or even 3 different colors. Okay? So if you can do that, maybe you do it that way. But again, you got to realize that this length right here is really this length. And this length right here is really that length, or similar to those lengths. Okay? Everybody got an answer? So let's see if we're right. They did E, G, F. So again, you don't have to necessarily do it in this, but then your E and F and other E have to be in the same spots. and then G, G, and F have to be in the same spots, and F, H, and H have to be in the same spot. Again, the order doesn't matter.
I'm not gonna do that right.
What did you do?
I did E, F, G,
E, F, G, okay,
S, H, G,
perfect.
and then E, F, H.
No, that last one should have been E, H, F. See how you went E, F, G? So this is, to me, when you look at this big triangle, that's the shortest side. So then I'm always thinking, what's the shortest side? And my shortest side in the little one is E to H. Okay? So again, if you can visualize that you have a small one, a medium one, and a large one, it helps, to me. Okay? Anybody need to see another one like that? Okay, so now we're going to look at this example right here. So now we're into theorem 8.2. Okay, so again, this might be something that you actually want to write down. I don't know if a lot of you write all these down all the time. Okay, so it says find C, D, and E. Well, if I start, I'm going to automatically always try to do what? Pythagorean theorem. Right? A squared plus B squared plus C squared, or equals C squared. I'm going to try to do that. But obviously, in my little triangle to the left, I only have 6. In my medium triangle, I only have 24. And in my big triangle, I really only have 30, my hypotenuse. Agree with that? So I only have one side of every single triangle. So then, I have to result back to this theorem 8.2. So in theorem 8.2, again, read it. If I draw the altitude has to be my geometric mean. So what's the altitude of the big triangle? E, right? So my geometric mean is going to be E. That means E has to be diagonal to itself. So I'm going to start with that. Right? Then it says, it is the geometric mean to the two segments that the hypotenuse split. So what are my numbers in my other diagonal? 6 and 24. So if I do 6 times 24, I get my answer is equal to E squared. So what's E?
12.
12? Everybody got 12? Everybody okay with 12? How they got 12? Okay. Now, we're actually going to learn another theorem. That would, you could do it another way. But, again, if I'm confident with my 12, I'm just going to use that and then do Pythagorean theorem. Okay? Because now I have, if I'm looking at this little triangle down here, now I have 2 of my 3 sides, right? So, again, D would be what part of Pythagorean theorem? D would be my hypotenuse. So C, 6 squared plus 12 squared equals D squared in this case, right? Which is actually C squared. Okay? Now, here's the other thing. If you ended up getting E to be not 12, meaning a number that has a decimal with it. So instead of the square root of 144, it was the square root of 143, for instance. I myself wouldn't use a decimal again. If you're going to use a decimal, here, right there, if you punch in the square root of 143 into your calculator and get a decimal, do not round that decimal. You have to actually use that entire decimal the rest of the way in the problem. So instead of using that, I would go back and use the square root of 143. So if I'm going to do Pythagorean theorem there, just for instance here, I would do 6 squared plus the square root of 143 squared equals, in our case, D squared.
Because it'd just be 143.
Right, because then when I take a radical times itself, I bust that number out and I just get 143 plus 36. But it's way more accurate than trying to do a decimal and rounding, because then if some people round, some people use the whole thing, it's a big difference. It doesn't seem like it'd be that big of a difference, but it is.
So in the theorem A2, where did that A come from that's on the altitudes? That's
I'm just showing you that that's letter A.
okay.
So in this case, that's letter E in that one.
Okay, so it's completely different from like the angle A because
Yes, sorry. I should have used totally different letter. I used A because it was an altitude. Put W in there. That's a good point. I don't know if you understood what he was asking, but that was a really good point. You know how we always said capital letters go with lowercase letters? That's what he was insinuating there. So it really should be W, but I used A because it was altitude. But that's a really good point. Okay? So then we could go and do C also, right?
Yeah, 12 squared plus 24 squared.
12 squared plus 24 squared, or now you could even do what D was, right? You could do D squared plus C squared equals 30 squared.
No, come on, that's.
Now it does? Okay, good.
So if they only give you like your W in there, would you just stop after you do like W squared equals X, Y, then?
Yeah,
You
you can't do it.
further?
You can't do it.
Okay.
If they only give you W, they have to give you one of these other things in order to do, especially this theorem right here, because I need 3 pieces, okay? Even though W is actually 2 of the 4 pieces, right? I can't do it with 2 variables in the other spots. Everybody understand what she's saying? Okay? Let's do, and I know you're saying we're doing way more than, but this is, for whatever reason, people don't like this. I'm just trying to, so, same thing here. If it says find E to the nearest 10th, am I even worried about this theorem right here? I'm just going straight to Pythagorean theorem. So again, anytime that you can do Pythagorean theorem, I think we're good enough at that now that that should just be able to lickety split, be done. Okay? We'll come back tomorrow and do the next theorem.
We do your test tomorrow.
No, I got a lot of people that still haven't taken it. So tomorrow we'll go over the test too then. C. Randall says C. Yes, sir. So we'll come back and do 8-3 tomorrow, and then you can work on your assignment, and hopefully you won't have any homework over the whole break. Wow, that's really nice of you. That's nice.
Thanks,
Yeah.
I appreciate it.
I gotta figure out what Drake did here to break this.